what kinds of questions are within scope for an in-class 2-hour exam. That was also open book. You could bring in notes but no laptops, same rules that I will be working under. So you can plan ahead to think about how you might want to go about bringing your material in and how you build an appropriate search tree to search through your material as you frantically look for answers. Okay, and I guess that's it, and then I'll just hand it over to Ashwin now.
Hello everyone, today we are going to talk about linear programming. So you have already seen two approximated algorithms for solving vertex cover for the normal time. Again, vertex cover is a set of vertices such that for every edge, I and j, either I belongs to S or j belongs to S. So we are trying to find the minimum size of set S that covers all the edges. So we have already seen two algorithms for solving this problem. Because it's NP-complete, we can't solve it in polynomial time. So we have to come up with approximation algorithms. The first one was a greedy algorithm, which gives you O log n approximation, maximum matching, to approximation. So, besides vertex cover, there are other interesting problems that we are trying to solve, such as SAT, set cover should be integer. So this is one of the constraints. And we have some inequalities in the form of sigma a I xi less than or equal to bi. We call these constraints. And unless we want to maximize the summation in the form of ci xi. It's a linear summation. So how can it help us solve vertex cover? So in vertex cover we have n nodes. Here we have n variables. So we represent each vertex with one node. So we represent each one of the vertices with one node. Each one of them should be either 0 or 1. And you can see why it's like that, because we want to say that if the vertex belongs to the set or not. So if the value of the vertex is 0, it doesn't belong to S, and if it's 1, it belongs to S. So we have some requirements for every edge I and j. I or j should be in the set. So we can rephrase it as xi plus xj greater than or equal to 1. So you can see how this is satisfied our constraint, because for satisfying this constraint, at least one of these should be 1. So at least one of them should be in the set. And at last, we want to minimize the summation over xi, which is the size of the set. So does any of you figured out some differences between vertex cover and linear programming, integer programming? Let's take a look at the integer programming. Can you see any differences?
I'm just kind of just intuition based on what you said. If in a vertex cover, if a vertex is in a cover, maybe it will have a value of 1. In integer programming, if it's not in the cover, it will not have a value of 1.
It can have a value 1. So it's the integer, and we can define this as for every x, the value should be greater than or equal to 0, and for every x, the value should be less than or equal to 1. So this is same as here. So we add some constraint. But there are other differences between these two. Yes. So here we want to maximize the summation, but here we want to minimize the summation. They are actually equivalent because, so for minimizing sigma ci xi, we are actually maximizing this summation, right? So they are actually the same. And here, we have less than inequalities, but here we have greater than inequalities. So also we can convert greater than inequalities to less than inequalities. How? By multiplying the formula minus 1. So we are just changing the multipliers. So as so far we have reduced vertex cover to integer programming. Also, there are other problems. For example, weighted vertex cover. So our solutions were just for simple vertex cover. So vertices can have weights on them. So what if our vertices have weights on them? The two previous algorithms, maximum matching and the greedy one, they don't help you. Right? Maximum matching and greedy were just can handle simple graphs without weights on the vertices. But here we have weights on the vertices, and I can give you an example to see the problem in the real world. So think that we have n potential locations for constructing gas stations. And there are some roads connecting these locations to each other. And we want for each road either this point or this point as a gas station. So for each point, we want to one of its endpoints to have a gas station, right? And the cost of constructing a gas station on each one of them is different. So we want to construct some gas stations here in order to minimize the cost and satisfy all our constraints. So as you can see, it's a weighted vertex cover. We have some nodes, and each node has some weights on it. We have some edges connecting them, and for each edges, one of the endpoints should be in the set. So, and we want to minimize the cost of constructing all of the gas stations. So can one of you write the formulation for this? Same as here. Here we have n vertices. x1 through xn. And each one of them can be 0 or 1, right? For each edge, I and j, either I belongs to S or j belongs to S, right? The only difference between the simple vertex solver and weighted vertex solver is that here we want to minimize Ci xi, which Ci is const of the construction of a gas station on vertex I, right? So just by changing the multiplier from 1 to Ci, we can handle weighted vertex cover. So anyone has a question? We want to reduce one more problem to integer programming. We want to show it's scalable, it can solve many problems. So we want to reduce SAT to vertex cover to integer programming. Sorry. So you know the problem of SAT?
I have a question on the previous page. So this problem CI, we want to find CI such that this is minimized, we want to find XI?
We want to find the values of xi, x1 to xn, which satisfies these inequalities.
Right, what is given? CI is given or XI is given?
Ci is given.
If
So we
CI
have the cost.
If CI is given, then we just put all XI to be 0, then there must be some other constraints, right?
Yeah. And these are the constraints. For each edge I and j,
Yeah.
xi plus xj should be greater than
Oh,
or equal to
okay.
1.
Thanks.
So do you remember SAT? How many of you know the SAT problem? Okay, so for those who don't remember, SAT problem is a conjunction of m clauses. Each one of them is a disjunction of 3 variables. And we want to see if there are an assignment to the variables that can satisfy this formula. So each of these variables is either true or false. And we want to find an assignment to satisfy this. So for satisfying this formula, each one of the clauses should be true, right? Because it's a conjunction. So each one of them should be true. We want to treat each one of them differently. So for each one of them, we have one constraint. One constraint like x1 plus x2 plus x3 greater than or equal to 1. And you can see how it satisfies the clause. So at least one of them should be 1. And 1 means true. So if at least one of them is true, then the clause is true. And if all of the clauses are true, the formula is true. So in IP formulation, we have xi's belong to set of 1 and 0. We have these inequalities. And what's the last part? Minimization, right? But here, we don't have anything to minimize. So we just set Ci is equal to 0 and minimize 0. So we don't care about minimization here. If you find an answer that satisfies all the inequalities, that's fine. That's all we need. So we set all the Ci's to 0. We reduced it to linear integer programming. So there is one other condition. We don't always have xi's here. We sometimes have x bar i's, xj, then xk. So how can we handle these classes? For xi bars, we can replace it with 1 minus xi plus xj plus xk. So if xi is 0, then this value is 1, and the value of this would be true. If x1 is 1, then the value of this will be false. So we have reduced vertex cover, weighted vertex cover, and SAT to integer programming. So you get kind of a sense that it can be really useful for solving NP-hard problems. So, any question until now?
So what's the goal of the last SAT problem?
What's what?
What's the goal of that? If you are able to list all the clauses and they kind of form a system of
So we want to find an assignment to the variables that satisfy this formula.
how do you write them as the sum of things, or what's your objective function?
So the summation here doesn't matter. We only interested in the constraints. So each assignment that satisfy all the constraints is an answer.
Okay, so you would end up solving the system of equations?
Yeah. For each clause, xi or xj or xk, we have this inequality that should be greater than or equal to 1. So any assignment that satisfies all these constraints, it's an answer to a problem. So now we reduce all these problems to integer programming, but integer programming is still NP-hard. Do you know why? Why integer programming is NP-hard?
SAT is NP-hard. SAT is NP-hard.
Exactly. Yeah. Because SAT is NP-hard and vertex cover is NP-hard. We just reduce SAT to integer programming. So integer programming is NP-hard too. But we want to find an approximated solution for this. Integer programming is NP-hard. So we want to make some adjustments to it so we can get the lower bound for the problem. You know, the two steps, getting the lower bound and then constructing an approximation algorithm. So the first step is getting the lower bound. And in order to get the lower bound, we make some changes to integer programming to get to linear programming. So what is linear programming? Actually, it's the same as integer programming, but the values can take any value. The variables can take any value. So they belong to R. So in integer programming, we have xi's belong to z. They should be integer. But here, they can be real. They can be any number. And again, we have n variables, and again we have some constraints in the form of this, and again we want to maximize the summation. The only difference is that xi's can be real. So how can this help us? We want to get a lower bound, but how can changing this would help us? Let's see an example in 2 dimensions. because it's simple. So let's say we have just two variables, x1 and x2, and they belong to real sets. And let's say we have three constraints. The first constraint is 1, 0, x1 plus 1, x2 equal to 0. So the first constraint is that x2 greater than or equal to 0. So what's the region that satisfies this inequality? x2 equal to 0 is here. So every point above it satisfies our inequality. So every point here satisfies this inequality. The next one is x1 minus x2 greater than or equal to 0. So x1 minus x2 equal to 0 is this line. So any point here below the line satisfy our inequality. So for example, this point, all the points on the line would be 0. Every point below it would be greater than 0. So here x1 is 1, and then x2 is 0. So 1 minus 0 is 1, greater than or equal to 0. So this is for the second constraint. And the third constraint is 2x1, 2 times x1 plus x2 less than or equal to 1. So what about this line? Let's draw it. This is the line. So this is the line. As you can see here, if we set x1 to 2 and x2 to 0, we get 2 plus 0 equal to 2. And here, if we set x2 to 1 and x1 to 0, we get 2. So we want to have x1 plus 2x2 less than or equal to 2. Is it below this line or why? Consider one point here, and we want to see if it satisfies the inequality or not. So here we have 1 and 2 times 0, which is 1 less than or equal to 2. So it's below this line, right? So the points here satisfy the inequality. So we want a region that satisfies all these three inequalities. So we get the intersection of these regions, which is this triangle, right? So any point inside this triangle or on the edge of the triangle satisfy all these three inequalities. And any other points doesn't satisfy at least one of them. So our region is here, right? And at last we want to maximize, let's say, x1 plus x2. So what does that mean? x1 is plus x2 is a vector in this direction, right? And we want to find the point in the region, in this region, that maximize the value of x1 plus x2. So you can see the vector. Let's look at the normal of this vector. The normal would be this line, right? So for every point in this line, 0 and 0, this value would be 0. Here, minus 1 and 1, this value would be 0. Here, 5 and minus 5, this value would be 0. So we can see for all of the points on this line, the value of x1 plus x2 would be 0. It's better to write. So what about this line? This line, the value for x1 plus x2 is 1. We can see here that for 1 and 0 is 1, for 0 and 1 is 1, for 2 and minus 1 is 1. And here, the value is 2, and here is 3. So we can see that all the lines have the same slope, but they are different in constant. And we only care about the constant. We want to find a line that maximizes the constant and has an intersection with this region. So we are trying, we start from this line in this direction. And we can see there are nodes here. So we push the line in this direction. So we push it in this direction. And then you can see there are more points in the direction of the vector. Then we push it more, and then we push it more, and we push it more until there is no points. Until we reach here. What is the intersection of this line and our region, our visible region? Is this node. So actually these nodes maximize this summation, which would be 2. Right? So we want to find the extreme point of the feasible region in this direction. Now we want to prove that the extreme point in any direction always lies on an intersection of 2 points, 2 lines. So again, we have our triangle here. We want to say for any summation like this, the extreme point is either here or here or here. And how can we prove this? So let's say the intersection is not on the line. It's not restricted by any lines. So, and let's say our vector, maximization vector direction is this. So there are points in our feasible region which are more extreme than this one. So this is not more extreme. contradiction. So we do this until we reach a line. Now, we know that extreme point is at least on one line. We want to prove that it's on the intersection of two lines. So let's say the intersection point is on this line, and the direction is again here. So one of these nodes, one of these points, have maximized this value and not this one. So we go in that direction, and we know as we go in that direction, the value gets greater and greater until we reach an intersection, right? So there are one other case, and the case is that the line is the normal of the vector. So any points on this line have the same value for this formula. So it doesn't matter. Any points that we pick is an extreme point. So here we just point the first or last point. So we have proved that any extreme point lies on intersection of two lines. And okay, so let's again look at our feasible region. Here we wanted to maximize in this direction. What if we want to minimize in that direction? So you remember here we said that minimization is equal to maximization. They are the same. So we want to look at the geometry perspective and see why is that. So if we want to maximize a value in that direction, we look at we try to find the extreme point in this direction. And if we want to minimize it, we look at the extreme point in that direction. So now we can see why they are the same. And why? Less than inequalities are the same as greater than inequalities. So for less than inequalities, the feasible region would be one side of the line. For greater than inequalities would be the other side of the line. That's why we don't care about this constraint. And if we had the constraint xi plus xj equal to bi, we can write it as xi plus xj greater than or equal to bi, and xi plus xj less than or equal to bi. We agree that these two are the same as this. So sometimes for feasible region would be null. Can you think of an example in two dimension? Just two constraints that their intersection would be null. What's the region for this? what's the region for this? Here. So we have two constraints that the intersection of them would be null. If you add any more constraints, still the intersection is null. So sometimes we don't get an answer. Sometimes the constraints are in a way that we don't have any solution. And there are some other situations that our feasible region is open from one side. Like this. So below this line and below this line is our feasible region, but it's open from this side. So we can go to infinity. And based on our vector, so if our vector is maximization vector is, the extreme point would be here. If it's our extreme point would be again here. But if it's this, our extreme point would be infinity. So that's why integer programming sometimes can't get an answer. Sometimes the answer, we have no answer, and sometimes the answer is infinity. So, and let's look at the d-dimension, geometric perspective of d-dimension. So for d-dimension, each constraint is a half space. So in the space, for example, in three-dimensional space, it's below this space. And all the other one is below this space. So we get the intersection of all these half spaces, and that would be our feasible region. So for example, this can be an example of a feasible region in 3 dimensions. And if you want to maximize the vector, maximize the points in this direction, this would be our extreme point. Now, why is it interesting that we reduce IP to LP to get the lower bound? Why is it interesting? Why does it work? For getting the lower bound, it should be solving polynomial time, right? So LP solution runs in polynomial time. And it's kind of difficult proof. If you are interested, I think the name of the mathematician that proved it was, he proved it in 1979. But in 2 dimensions, it's kind of easy. Let's again look at the triangle. So we said that intersection of all lines are potential for our solution. So we have to just look at the intersection points. Right? How many intersection points do we have? We have n lines, n constraints. How many intersection points? Exactly. N choose 2, which is roughly n squared. So we check all of these n squared points, and we look for the maximum value. So it's in polynomial time. We get the intersection points, and to the power of 2, we look at all of them. We put them in the maximization formula, the summation. Each one of them gives us one value. And we pick the maximum value. And actually, so since here we have something like convex, the intersection point would be n. So it's better, even better. But let's say we get all the intersection points, there are at most n2, so it can be solved in polynomial time. But I said earlier that the proof is very difficult. Why is that? Because this won't work for d dimension. For d dimension, how many intersection points do we have? N choose d, which is roughly n to the power of d. And this is not polynomial, this is exponential. That's why this proof won't work. But there is a proof for this, and it can solve linear programming in polynomial time. Any question? So as we said earlier, we want to find the lower bound. Again, look at the triangle example. We want to find the lower bound for our solution. We reduced IP to LP to get the lower bound. What's the feasible region for LP? It's here, right? So our LP looks for a solution in this region. But our IP solution looks for points with an integer value. So it looks for this point, this point, this point, and here. So it's not actually the same. Our LP solution is in this region, which, let's say we want to maximize it in that direction, gives us this point. So LP solution is this point, extreme point in this direction. What about IP solution? IP solution would be that point, right? So we can see that this point for maximization is an upper bound for that point. And for minimization, it's a lower bound. So we have got our lower bound. LP solution always is a lower bound for the IP solution in case of minimization. So in vertex color, we want to minimize the summation over xi's, right? So LP gives us the lower bound. So we are done with the first step. We have the lower bound in polynomial time, so the first step is done. The second step is getting an approximation algorithm to give us an approximated answer based on this lower bound. Is there any question? You seem a little bit confused. So is it clear?
The integer solution, the 0, 0 is not an integer solution. Why?
That's my mistake. Let's say in that direction. In that direction, we want to maximize, then the linear programming solution would be this one, and integer programming solution would be this one. And this is an upper bound. Because we want to maximize, this is an upper bound. And if we want to minimize in this direction This would be LP and this would be IP, so it's a lower bound. So again, let's look back to the vertex cover problem. So we want to minimize the summation xi, yeah? And linear programming gave us an assignment to xi's that minimize this summation. What's the assignment? We said that for each xi, it should be between 0 and 1. So let's say we get 0.7, 0.5, 0.2, 0.25, and this, right? What should we do with this? We are trying to find if that vertex belongs to the set or not. So we want values either 1 or 0. But we have fractions. What can we do with these? So we want to round it. How would you round it? If you round all of them to 0, so we have no vertex in our set. If you round all of them to 1, so the complete graph would be our set. It's not a good answer. So how should we come up with a good rounding process?
So the minimum difference between the number and the integer, 0 or 1. The minimum difference between the number and the integer, 0 or 1.
So actually you are saying that if the value is greater than or equal to half, and if it's less than half, replace it with 0, right? So why does this work? As you remember, so this is our integrality constraint. So we know each value should be either 0 and 1. But we have other constraint. Xi plus xj greater than or equal to 1. So we have 0.7 here, and we have 0.4 here. We have replaced this to 0, and replace this with 1, right? Why does this work? We still want to satisfy all the constraints. Does that always work? Let's do some math. So, let's say x prime is our value after rounding. So x prime is 1 if xi greater than or equal to 1 over half, and 0 is xi less than 1 over half, right? So, xi prime, in this case, is equal to 0, is less than 2 times xi, which is equal to, which is less than 1, right? So 0 is less than or equal to every positive number. And here, in this case, x prime I is equal to 1, which is 2 times 1 over half, and we know xi is greater than or equal to 1 over half, so it's less than or equal to 2 times xi, right? So, in any case, always, x prime I is less than or equal to 2 times xi, right? Let's hold for a second. So in here, we wanted to satisfy all these inequalities. So we know at least one of them should be greater than or equal to 1/2. Right? So we can have a constraint xi plus xj greater than or equal to half, while xi is less than half and xj is less than half. So the summation would be less than 1. This cannot happen. So at least one of them is greater than or equal to half, which we rounded to 1, so at least one of them is in the set. So this rounding satisfies all the inequalities. And you can see why. Any question? So, we have done the reduction to LP. LP give us an assignment to x1 to x1, which is xi belongs to R. We round it, and now we have the IP solution. Right? Now we have the IP solution that satisfies all the inequalities. But this value is not different. We rounded the variables, we changed the variables. This value is now different. So that's when we want to get an approximated answer. So we have the lower bound. So let's say the solution for LP is S, which is sigma xi, but now we have sigma S star, which is this. So this is the lower bound. This is the IP solution. So as you remember, the first step was getting the lower bound. The second step is finding an algorithm that gives an approximated answer based on this lower bound. So we want to see how far is that from the lower bound. So how far is that? S star is sigma xi star. We already seen here x star is less than or equal to 2 times xi. And here, so the summation is less than, because each one of them is less than or equal to 2 times xi, the summation would be less than or equal to 2 times xi, which is 2s. So S star is always less than or equal to 2 times s. That gives us 2 approximation. So we guarantee that always our IP solution, it's less than 2 times the lower bound. It's at most 2 times of the lower bound. So we are done with this step 2. Is there any question? The first step, getting the lower bound, we reduce the problem vertex cover to integer programming. So for getting the lower bound, we reduce IP to LP. we get the lower bound in LP, then we round it, which is our algorithm, approximated algorithm. We round it and we get another answer. The answer is different than the other one, but it's always less than or equal to 2 times of the lower bound. So that's the approximate solution. Any question? So what are our 3 steps? The first step is write an IP formulation. We did that for vertex cover, weighted vertex cover, and SAT problem. We did the first step. Then relax it to LP in order to get the lower bound. So this is the second step. If we relax the SAT or vertex cover or even traveling salesperson or set cover, we get the lower bound for all of them. So we don't need to do anything. We just write an IP formulation, then we reduce IP to LP, we get the lower bound, and that's all. And the third step is the rounding problem. So we know IP is integer, LP is real, so we round the real variables to integers. And so the third step is rounding. And get back to IP solution. First is writing an IP formulation, then reduce it to LP, get the lower bound, then round the LP back to IP, and approximate based on the group. That's all the 3 steps for linear programming that helps us solve these NP-hard problems in polynomial time, give an approximated solution.
What problems does this work and not work for?
So it works for, as I said, it works for vertex cover, weighted vertex cover, set cover, traveling salesperson, and many other problems. But so writing an IP formulation for many of them is really difficult. So for set cover, it's easy. For vertex cover, it's easy. We have one edge. One of them should be in the set. So it's just this. For SAT, it's just this. But for traveling salesperson, it's very difficult. And for some of the NP hard problems, they couldn't find any way to write the formulation, IP formulation. But this is still a good tool because it's solved many of the NP-hard problems. Actually approximating that solution.
Another question is, we have to worry, or is there some example where we have to worry about the size of the representation after the transformation? So
Size of the
in general,
constraint.
if you can perform a transformation like this, can you always get a polynomial time approximation?
Yes. So you have x1 through xn, right? You have n variables, but you can have many constraints. So we don't have any bound on constraints.
So the number of constraints doesn't matter in the runtime analysis.
Actually, Vijay, that's not true. You have to have a polynomial sized code. Right? So So if the way you formulate the integer program causes you to have exponentially many constraints, that potentially could be a problem. It turns out it's not a problem as long as you have a way of saying, given a solution, is there a constraint that's validated? So even if you have an exponential number of constraints, as long as you don't write them down explicitly and you have some procedure that says, hey look, this one got validated, there's actually a way to solve the problem. And Kachian's original algorithm for linear programming does precisely that. So often you have a situation where you have an exponential number of variables and a polynomial number of constraints, and there's a way to flip it. So now you have an exponential number of constraints, having a polynomial number of variables, and then you can solve the LP as long as there's extra oracle.
Check it afterwards.
Right. Well, as long as you have this oracle, I can say, given a possible solution, is there a validated constraint required? That runs in bulk. If you can do that, then you're okay. So for TSP, for example, so some of these problems, the easy IP will have an exponential number of constraints. But again, if you can build this oracle, it's not a big problem. The second thing is that while you can always make the LP formulation, often the hard part is doing the rounding to guarantee that A, you still have a feasible solution, and B, that the feasible solution has any decent approximation. Sometimes the approximations can be terrible. So you won't always get nice constant factors, but the procedure always works. But for different problems, obviously, because they're harder, you'll get good answers or bad answers. Just to ask that one question.
So when you showed that we get a 2 approximation, what problem was that for? Exactly, was that for SAT specifically?
For what?
So you showed that we get an approximation with a factor of 2.
For
So that was for SAT, right?
No, for vertex count.
Oh, for vertex count, okay.
So because in SAT we don't minimize or maximize anything,
Right.
we don't have that. So yeah, that's true. Number of constraint just shouldn't be exponential. So in polynomial, we can't have anything. So the first step is writing an IP formulation, the second step is LP, and the relaxation, and the third step is rounding. We've seen the deterministic rounding. We have said that if xi is greater than or equal to 1/2, then replace it with 1, otherwise replace it with 0. That's deterministic. But deterministic always won't give you a good answer. And the example is set cover. So let's define set cover. We have a number of sets, S1 to Sn. Each one of them contains values from x from this set. So, for example, S1 can be x1 and x4 and so on. So we want to find the minimum size number of the sets that can cover all of the variables. So let's say S1 is x1 and x4, x2 is this, and S3 is x1 and x2. x3 and x2 and x3, right? So S1 and S2 can cover all of the variables. We have x1 here, x2 here, x3 here, and x4 here, or here. So we don't need all the 3 of them. So we want to find the minimum number of sets that cover all of the variables here. Again, the first step, IP formulation. We have x12, xn,
which represent, what does they represent? What's the best way to define xi's? To be variables or sets? Sets, yeah. Because, so xi's represent set I. Because xi is either 0 or 1. We want to know that if we choose this set or if we don't choose it. So what are the constraints for every xi? Let's change the formulation. Let's say there are a1 to an. Right? Si is actually the xi here. I changed the notation to be more relevant. So the summation of si's is greater than or equal to 1. So, and we know each ai belongs in at most k sets. So this summation is like S1 to Sk is greater than 1. So again, like vertex cover, here we said that at least one of them should be greater than or equal to 1/2. So here at least one of them should be greater than or equal to 1/k.
You mean summation of x1 plus x2 plus
Yes,
x.
yes. I changed the notation to be more. Yeah, the summation of xi's here are greater than or equal to 1. So one of the sets is at least 1/k. So again here, our rounding algorithm is pick set Si if the Si value is greater than or equal to 1/k, and if it's less than 1/k, don't pick it. Same as the vertex cover. And same as the vertex cover, sigma xi is less than or equal to sigma ksi, which is k times s, and s is our lower bound. Right? So here we get the k approximation algorithm. But it's not very good because k can be roughly n. So it will be n approximation. It's not a good solution. The deterministic is not giving us a good solution here. Because we said that k is the number of the sets that each variable is in. So let's say all of the variables be inside all of the sets. So k is roughly n, and then this gives us an approximation, which is not good. That's when we try to use randomized rounding. So the deterministic won't work, so we want to try randomized rounding. So here again, we pick each set with probability of Si greater than or equal to 1/k. So for, it's like, and here otherwise. For picking a set, we toss a coin. If it's less than 1 over k, we don't pick it. If it's greater than or equal to 1 over k, we pick it. So is that clear? We write the IP formulation for the set cover. We reduce it to LP. We get the lower bound. We get a vector of SIs, which is not integer. And then we want to round it. This is the last step, the third step. So we want to round this. Deterministic won't work, we do it randomized. We have the value for all of them, we toss a coin. If the value is greater than this value, we pick it, we put Q1 here. If it's not, we put 0. So it's kind of probabilistic. But what would we look for here? So we know always, when we try to round, we look for the constraints, because we should satisfy all the constraints. We are changing the variables, the constraint may change, but we want to satisfy them. So here we cannot, because it's randomized, we cannot make sure, but with a good probability, we want to say that all the constraints will be satisfied. So what's the probability that one AI wouldn't be covered?
In the case that in your coin toss snow has turned out, you won't have a one.
So it's not covered when?
And the K coin tosses result in chaos. All
Yeah.
of them.
So if we get this right for all of them. So we said that AI belongs to S1 to SK. And the worst case is that we don't pick S1, we don't pick S2, and we don't pick SK. And we know that S1 plus SK greater than or equal to 1. So it can be proved that the worst case for this formula is that all of them are equal to 1 over k.
So is there SI a probability now?
AI? No, SIs are the probabilities. SIs are the values from the LP programming. And we toss a coin with that chance. If we get the chance, we pick that set. If we don't, and we don't pick that set. Let's explain it in a second. So we get these values, right? S1 for set S1, and S10 for set S from the LP. So each one of them is something, some fraction as vertex cover. So we get a fraction. Yeah, so we get a fraction, and this represents S1 and this represents Sn, and for each one of them, in probability S1, we pick that set. So if we doesn't cover AI, then this is the probability that we doesn't cover AI. And the worst case is when all of them are equal to 1 over k. So the probability is 1 minus 1 over k to the power of k. And so, which is roughly 1 over e. So, if we pick, so there's no time, I'm getting stressed. So,
What
If-
if you next?
yeah,
Already passed all over.
yes, yes. So yeah, let's keep it here and we can continue this.